Quick revision video on ionic bonding, and be sure to subscribe for new content. Okay, so we'll start with the essentials. Ionic bonding occurs between metals and non-metals. Metal atoms lose their outer or valence electrons, and they do that to achieve a noble gas structure. And as a result of that, they become positively charged ions, also known as cations. Non-metals, they gain electrons to achieve a noble gas structure, and they become negatively charged ions, which we call anions. And finally, the ionic bond is defined as the electrostatic attraction between these oppositely charged ions. So we'll move on to dot and cross diagrams now. These are the diagrams we use to represent ionic compounds, and they show the particles or the ions present. So we've got three to do: potassium fluoride, magnesium chloride and aluminium oxide. So if you want to have a go at those, pause the video and then play on for the answers. So potassium fluoride first, you can see from the formula the ratio of potassium to fluoride ions is 1 to 1. So the potassium ions represented like this. So you can see I've got 8 crosses. So there was an electron in the outermost shell, that's gone. It's given the ion this positive charge, and we're showing the 8 inner electrons, so that's a full outer shell there. Now you can draw this with no electrons in the outer shell if you want, but I prefer to show these electrons here. And of course you could have used dots. I've just chosen to use crosses for the metals, I think, in all the diagrams. So moving on to the fluoride ion now. So if you think about fluorine's position in the periodic table, it's in group 7. So because I've used crosses here, I'm using dots for the fluorine electrons. So we've got 7 of those, and then that cross there, that's obviously come from the potassium, and so we represent it with the different shape. And obviously don't forget your charge. And you'll notice also square brackets are used for ions. So magnesium chloride now, we've got 1 magnesium ion, but we've got 2 chloride ions from that formula. So the magnesium ion is shown like that. Just be careful you get the correct charge. Don't forget your square brackets. And we're going to draw 2 separate chloride ions, so very similar to the fluoride ion, but we draw 2 of them. And then finally, aluminium oxide. So we've got a ratio of 2 aluminium ions to 3 oxide ions. So there's the 2 aluminium ions. So don't forget that 3 plus charge in the square brackets. And we're going to draw 3 separate oxide ions like that. So you can see we've got 6 dots because oxygen is in group 6. It's got 6 outer electrons of its own. And then the 2 aluminium ions, each one gives away 3 electrons. So each oxide ion gets the 2 electrons it needs, and obviously that equates to those 6 electrons. And of course we've got 2 minus charge for each ion. So if we move on to the structure of ionic compounds now, so when oppositely charged ions attract, they do so in all directions, and that leads to the formation of a giant ionic lattice, which will contain billions and billions of ions. And all ionic compounds form giant ionic lattice structures. So simple representation of a giant ionic lattice is something like that. This one's for sodium chloride. So if I just focus on that central chloride ion there, you can see it's attracting sodium ions in all directions. And finally, the ionic formula, so something like NaCl for sodium chloride, that shows the formula unit. So that's the ratio of positive ions to negative ions. The actual formula, there would be billions of sodium ions and billions of chloride ions, but the ratio is 1 to 1, so therefore we get the NaCl formula. So we'll finish with the properties of ionic compounds. We're going to look at 3 classic properties of ionic compounds. The first one, melting and boiling points. So it takes a very large amount of energy to overcome all those strong electrostatic forces of attraction between the oppositely charged ions in the giant ionic lattice. So as a result of that, ionic compounds typically have high melting and boiling points. Moving on to solubility now. So many, not all, but many ionic compounds dissolve in polar solvents such as water. So in a water molecule you've got the oxygen atom, which is slightly negative. It's not a full negative charge, it's a slight negative charge, and we represent that with a delta minus. And the hydrogen atom is slightly positive, so we represent that with a delta plus charge. So when you place an ionic compound in water, the oxygen atom of the water molecule, remember that's slightly negative, that's going to be attracted to the positive ions of the ionic compound, so the metal ions, and the hydrogen atoms, remember they're delta positive, they would be attracted to the negative ions of the compound, the non-metal ions. So if the ionic compound is going to dissolve, if it's soluble, the attractive forces between the water molecules and the ions are going to overcome the attractive forces between the ions. And finally, electrical conductivity. Basically, in the solid state, the ionic compounds can't conduct electricity because the ions can't move. The most common mistake I see is students say electrons can't move. So for ionic compounds, it's the ions' ability to move or not move which is going to determine whether they conduct or not. So in the solid state, they can't conduct, whereas in the molten, so when you melt ionic compounds or you dissolve them in water, ionic compounds do conduct electricity because the ions, not the electrons, can move.